Wonderful. All right. Good morning, everybody, and welcome to this second part of our short Neo4j Generative AI workshop series. We're back today with a workshop today, so I'm very excited to welcome you, everybody, to join this session. Obviously, foremost, I'm super happy to be working today together with, excuse me, Martin O'Hanlon, who is our technical curriculum writer and curriculum developer at Neo4j, who's building these amazing workshops that are all published on our Graph Academy page. And one of those will be running together today with you all. So as you know, this is a mix of some lessons, a little bit of hands-on. And we try to make it interactive so you can follow the lessons, but you can also ask questions. You can let us know how it works. So just use the Q&A function for that if you like. You can also use chat, but chat might be a little overwhelmed at some point. So please, if you have any questions, anything you want us to look into, please use the Q&A function and send in your questions there. But you can also use chat for anything. Just tell us where you're from, where you're watching this now, and what's maybe your top thing you're working on with AI and maybe graphs already. So that would be nice to hear. The session is recorded, obviously, so we will record the session. If you are missing something or you want to watch something again, then obviously we will share the link to the video afterwards, and you can look back into it. And all the other materials you also get by email over the next few days. So the workshop course itself and some other things, so you can follow that along afterwards as well. But yeah, I think I'm excited. I think it's going to be a fun event today, fun workshop this morning. Handing it over to you, Martin.
Thank you very much, Alex. Thank you all for coming and welcome. We are going to look at GraphRAG today and generative AI and how we can use Neo4j. So just a few kind of points of note. If I'm looking this way, I'm not ignoring you. This is where the questions are and any chat. If I'm obviously looking this way, I'm doing and running the workshop as well. Okay, brilliant. So let's just go through a couple of slides. So first of all, thank you, Alex. My name is Martin. I work in the developer relations team at Neo4j. You can find me almost everywhere online with at Martin O'Hanlon. I'm pretty easy to find. And it'd be great to connect with you. So what are we going to do today? So we have got a sort of 4-part workshop that we are going to do today. We're going to have a look at what is generative AI and how we can use Neo4j and graphs to improve our generative AI experiences and applications. We're going to look at how we could create knowledge graphs, so how we can turn unstructured data into graphs, and we're also going to look at retrievers. And the final section is around using agents, whereby you can integrate the retrievers that you have created that use your knowledge graph into an agent. And that's the bit that I'm going to leave you to kind of do as homework after the session. So first off, we are going to be using Graph Academy. So Graph Academy is Neo4j's completely free online training platform where you'll find lots and lots of courses that will help you learn about Neo4j, generative AI, and the graph ecosystem more generally. So yeah, we are going to use Graph Academy for this workshop. So what do you need? Well, so first of all, you only really need 2 things. You need the workshop material, which you can find on Graph Academy, and you will need a Graph Academy account. So if you go to graphacademy.neo4j.com, you can create an account there if you don't already have one. You can log in with Google or LinkedIn, all of those sort of other options as well. You're also going to need access to the workshop material, which you will find at graphacademy.neo4j.com/courses/workshop GenAI. To help and support this, I have put all of the links in this document here, and what I will do is I will somehow Alex, I don't have the power to create a sticky note. Would you be able to do that for me just with that link? So if you go to the link I've just shared shared in the chat that hopefully Alex will put as a sticky note. dev.neo4j.com/workshop-GenAI notes. You'll get to this document here. Thank you, Alex. You'll get to this document here, and this has all of the links that you're going to need. So it's got the link to Graph Academy and the link to the workshop material. It's also got an OpenAI key, which we will be using later within the session. So I'll go through the same process as well. So if we go to Graph Academy, we're going to end up here. So I'm just going to sign out, and I'll go through the process as well. So this is Graph Academy. I'm just going to sign in. You can sign in with a Google account, or if you can create a username and password, Microsoft, GitHub, whatever. I am going to sign in with my Google account. And it's going to take me into Graph Academy. There we go. And you're going to kind of see a dashboard. I have all sorts of things going on, but we can see all of the courses. Once you have a Graph Academy account, if we go to this link here, neo4j.com, Graph Academy, neo4j.com courses, GenAI workshop. This is going to take us to the workshop material. And there we go. And this is the workshop that we are going to run through today, Neo4j and Generative AI workshop. I will just give people a second just to go through that. Again, Alex, thank you very much for putting the link as a sticky note. Paco, I am incredibly sorry that your company bans access to that link. I can only assume you can't access neo4j.com at all. Feel free to follow along. I will go through all of the activities. So if you can't actually join in and participate, please follow along as well. Paco, I've realized that what you might not be able to gain access to is the Google Doc where all the links are shared. So what I will do is I will just pop them into the chat as well, the two individual links that you're going to need. Okay, so I can see that people are starting to join. So I'm just going to go off and enroll in this course. So this is the workshop that we are going to do. Once I enroll, we are going to go through each of these modules. To navigate Graph Academy, there's a little menu up in the top left-hand corner, and we can see the 4 modules that we're going to do today: Generative AI, knowledge graph construction, retrieval, and agents. I've got a few things to say to kind of talk about, so I'm going to get started, and then obviously join Graph Academy and enroll in the course, and you can follow along as well. So the way that this works is that there is a series of lessons, so you have access to all of the content that I'm going to present. I have a slightly different view, so I have a slide view, but it's exactly the same content. So before we get into the kind of practical activities around GraphRAG and using Neo4j, it's worth spending a little bit of time just confirming what we probably already know and talking about what some of the challenges are with generative AI. So GenAI refers to artificial intelligence systems designed to create new content that resembles human-made data. And the way that they work is we take a huge amount of training data, whether that's images, text, audio, code, or mixture of, use that data to create a model, and then that model can then generate new output which resembles the training data it was given. They're not intelligent in the way that humans are. They do not understand or comprehend the content that they generate. They rely on statistical patterns. So while it may look coherent and relevant and right, there's no understanding there, right? And that's an important limitation of using generative AI. So we are going to focus today on large language models, or LLMs. So LLMs are text generating GenAI models, and they generate particularly text and data. And the way that an LLM works, the way that a text generating GenAI model works, is essentially it is a continuation of the instruction that it receives. So if presented with continue this sequence ABC, an LLM could respond with DEF. Now, obviously, our instructions can be significantly larger than that, and our responses can be much more sophisticated. But that's essentially how it works. It continues the prompt. So our prompt can be as complicated as we want, but it should specify requirements and provide clear instructions on how to respond. That gives the LLM the best chance of generating a response that makes sense. We should have caution in using generative AI and LLMs, right? Highly predictive text machine, highly complex text predictive machines. They don't understand, and they also can't describe, how did you answer that question? I don't know. There is no correlation between the question that was answered and the response that was given. They also have limited access to data. So that training data that we looked at is often publicly available. Data, internet, books could be of questionable quality. And it also happens at a point in time. That training data is static and it may not reflect the current state of the world. So if we ask it things like, tell me about the latest features about Neo4j, if we give it no other information other than its training data, here are some old features with incomplete information. They are also designed to create human-like text and often fine-tuned to be as helpful as possible, which occasionally means generating misleading or baseless content. And we call this a hallucination. I like this example. If we trained an LLM with enough information that described the moon as being made of cheese, it would respond with the moon is made of cheese. So we can improve the accuracy of our LLMs by providing additional information or context in our prompts. So let's say we want an LLM to summarize a company's results. It could use its training data, which would be immediately out of date. However, if we provided within our prompt some additional information, like a stock market report, the LLM could use that information to provide a better response. The more information we give, so if we're looking to answer specific results, so for example, summarize this company's results. Again, if we provide it with the annual results, it's going to do a much better job of delivering the right information to us. So we are going to spend a lot of time thinking about how we supply context, right? And supplying context in our LLMs helps them be more accurate, relevant, trustworthy, reduces hallucinations, and compensates for that lack of access to data. That's our challenge. How do we provide good context? Okay, so we are going to move on to lesson number 2, and we're going to talk a little bit about GraphRAG. So before we talk about GraphRAG, let's talk about RAG, or Retrieval-Augmented Generation. So RAG is an approach that enhances the responses of LLMs by providing them with relevant, up-to-date information retrieved from external sources. RAG allows us to supplement or provide additional context to our LLMs to get a better response. And the process generally works like this. We look to have a question. We have an application whose job is to understand that user's query, to retrieve additional information, and then to use that additional information to enhance the prompt that it sends to the LLM. Henceforth, we get a better response. That is the typical process. And our RAG systems can be as sophisticated as we need them to be in order to provide good context. So if we use this idea of what's the latest news on the Olympics, our LLM, based on its training data, is not going to know the answer to that question. However, we can create a news chatbot which uses an API to pull back real-time information to provide grounding to our LLM to then get a better response back. And the key component of this RAG process is the retriever. So the retriever's job is to say, okay, well, what question was I given? how can I search additional information that allows me to get the good context back? And typically a retriever takes unstructured input like a question or a prompt, and it searches for structured data. That's its job, and it is a key component in it. And Neo4j supports various ways of building retrievers, so full text search, vector search, and text decipher. And we're going to explore these methods in this course. So our RAG process, our retriever is that key component, and it can take its data from anywhere, whether that's documents, APIs, or knowledge graphs, right? And we can use a mixture of data sources to allow our API to deliver better responses. And a knowledge graph provides a great way of doing that. It provides a mechanism of providing a structured data source that can contain articles, news, whatever we think is appropriate in order to be able to provide our LLM with good context. So, RAG, GraphRAG. So GraphRAG, graph retrieval augmented generation. So we can use GraphRAG in conjunction with RAG, and it basically is an approach that uses the strengths of graph databases to provide relevant and useful context. So VectorRAG uses embeddings to find contextually relevant information. GraphRAG enhances this process by leveraging the relationships and structure in the graph. All right, so benefits of GraphRAG. This is essentially what we are going to explore during this workshop. Better context, improved accuracy, explainability, flexible queries, and enhanced reasoning. Those are the things we want to achieve. And if we look at a simple approach towards GraphRAG, it's to use a combination of vector search and graph traversal. So if we use the same model that we looked at before, a user submits a query. Our application uses a vector plus graph retriever to find similar nodes. So it uses that prompt to find similar information, and then uses those similar nodes and traverses the graph around those similar nodes to find related information. And that delivers us a more complete context, and almost always a more relevant context for the question being answered. We can also use full text search, and we can also use a process called text decipher as well. So text decipher, an alternative approach in GraphRAG, essentially where we have a question, we use an LLM to generate a cipher statement based on a schema and the question, which we can then execute against our graph to return results. And we can use a combination of all of these techniques. Okay, so the last bit of me talking is I want to talk about knowledge graphs. So we have mentioned knowledge graphs. One of the things that we are going to do is we're going to build a knowledge graph through this workshop. So knowledge graphs provide a structured way to represent entities, attributes, relationships between them. And they are incredibly useful for GenAI applications because they provide structured data, but it is incredibly flexible structure. So structured, but also flexible. If you've not heard of the term knowledge graphs before, they're not a new thing. Search engines typically use knowledge graphs to provide information about people, places, and things. So if we imagine this as a knowledge graph about Neo4j, Neo4j was founded and is located in Malmö. It's also located in London. London happens to be the capital of the United Kingdom. Neo4j, the company, is the owner of Neo4j.com, the website where various documentation and blog posts are blog posts are written. Blog posts refer to things like database technologies. So we have this very flexible structure that can define facts about things. Knowledge graphs, super helpful to break down sources of information as well. So if we have multiple sources of information, we can chunk them into smaller pieces, and we can understand how those chunks relate to each other through things like topics. Again, very flexible structure that allows us to model data in this way. Great thing about a graph is doesn't have to just represent the domain data, the data itself. We can also use that structure to describe what the data is and things like organizing principles. So if we think about Graph Academy has content and courses. That content has a type, so things like quiz, challenges, videos, and practical exercises. So we can use that single structure to define what the data is, and how it is organized as well. Yeah, and you can continue that model on, so on and so forth. Okay, so in general applications, knowledge graphs play a crucial role in capturing and organizing important and domain-specific and proprietary information. Because of this flexible structure, they are not limited to structured data. We can also integrate and organize less structured information, more unstructured data. Okay, right. That is enough of me talking. We have spent some time going over some principles that are going to be helpful for us to give us context and information when we move into the kind of practical side, which is what we're going to do now. Okay, so we are on this lesson here. So we're in this first module in this GraphRAG for Python lesson here. So your job is to create a dev environment that we are going to use throughout this workshop, and we're going to run through it together. Now we're going to use the GraphRAG for Python package, which is going to allow us to create retrievers and knowledge graph construction pipelines and GraphRAG pipelines as well. Now, to get started, I have created a repository. It's at github.com, Neo4j Graph Academy. So it's this one here, this repo here. It's got all the starter code in and resources that you are going to need. Now, you can use a GitHub code space, and I would recommend that you do. So a GitHub's code space is an online IDE and workspace for this course. You're not going to need to install anything on your machine, and all you need is a GitHub account. If you want to develop on your local machine, you can do. All right. So this point, it's over to you. Right, I'm going to run through the same process as well, but what I would like you to do is run through this section to get started. So we are here, module 1 on this GraphRAG for Python lesson. I'm going to use a GitHub code space and go through. There are instructions to develop on your local machine, and then we need to set up an environment. But let's get started just by opening up a code space. So follow this link. We're just going to create a code space. It's going to clone everything for us. Code usage is paid for by me. It is, however, the free monthly allowance is something like 120 hours. We're not going to use anything like that. So you won't actually have to give any money out. So let's go. I'm just go off and create that code space. And it's going to take a little while to spin up. As we kind of see, we get, want of a better word, VS Code in a browser. And it's going to go through and clone that repo. Like I say, it'll take maybe a minute, maybe 2 minutes. Once it's cloned the repo, it's also going to install any of the prerequisites that we need. So I'm going to take this opportunity just to kind of look through, look at comments and questions and see what's been going on, if anything. So I'll just leave that. Okay, so there's no questions, which is great, right? Please, if you do have things that you want to talk about, or if there's things that that you think are interesting, please please ask questions. Okay. So we have a few people. Hi Simon. Hi from Amsterdam. Hi from the UK. And okay, brilliant. If you haven't done so already, there is a poll that we have submitted. It would be great if you could complete that. The poll just allows us to just understand why people are here. It's really helpful to us. Okay, right, so my code space has opened. It's opened my remote. It's cloned the repo. What you're going to see in a moment is that once it's cloned the repo, it's going to go off and it's going to install all the prerequisites. You'll see a script running down here. But once my code space is open, what I then need to do is I need to set up my environment. So this information here is the connection to the Neo4j database that has been created for you when you enrolled in the course. This information is specific to you, so you have your own connection details on your screen right now. So what I'm going to do is I'm going to go off and I'm going to create this environment file. So I'm going to create a new file. I'm going to call it .env. Oh, we can see that our code space is just installing all of our prerequisites. And I'm going to copy in my connections to my Neo4j database. Now, we also need an OpenAI key to complete this workshop, which we can get from that document that I shared earlier, which is just here. And then I place that in there, and I have my OpenAI API key. I am share my OpenAI API key. Now, once I've set up my environment file, there is we can test our setup. So there is a program called testenvironment.py, and if we run that, this will attempt to connect to our Neo4j sandbox and the OpenAI API key. And if everything works, we should see okay. So once I've got the test environment open, I can run it. So I run my Python file, and it's going to go off and run the test to make sure that everything's set up correctly. And finally, I will get back, hopefully, something that says, okay, there we go. Ran 5 tests. Okay. So what it's done here is it's connected to my Neo4j instance that was created by Graph Academy for me. It's connected to OpenAI. And we are in a position now whereby everything works. I often describe this as the hard bit. You know, creating an environment can be quite difficult. If I could get some feedback, is this sort of... Richard asked a question: enterprise management users must pay for their code spaces usage. Yes, even as an enterprise managed user, which I am as well, you still get a free tier. If for whatever reason, I don't know, maybe your enterprise has restricted access to code spaces, I'm not sure if that's even a thing you can do. You can install on your local machine as well. Okay. But once we have got everything set up and ready, you should, like I say, when you run this test environment file, it's going to run through those tests and set everything up. Things that I see people get wrong quite often is, so for example, if we don't call this .env and we just call it env, we run the test environment file, it's going to fail first of all and says env files does not exist. Yeah. .env. If you've got any information wrong in here, I don't know, maybe something like that. We run our test environment file. Again, we see a failure. Neo4j database query failed because I gave it the wrong name of the database. Okay, there are a few things that I need to do. So I'm going to continue on. So our first module is around knowledge graph construction. So we are here, we're going to knowledge graph construction on the second module. So what we're going to do here now is we're going to go through the process of creating a knowledge graph using generative AI from unstructured data. And the way that we construct knowledge graphs from unstructured data looks like this. So it's a 5-step process. So when we're going to create a knowledge graph, we typically want to go through 5 processes. First of all, we need to gather the data. We need to put it somewhere, or we need to get it out of, I don't know, proprietary storage, whatever. We need to find it and gather it. So we need to gather our data. We would typically look to chunk it, right? So let's say it's documents or websites, or we would typically look to chunk it. So it tends to be very long documents. We would chunk it into smaller pieces to make it more easier to manage. We may then look to vectorize the data, so to create embeddings from it. Once we have our chunks data, we would then pass that data to an LLM to extract the nodes and relationships from that text, and we would then use the output from the LLM, which basically says, here are nodes, here are relationships, to generate our graph. So if I go through an example, let's say we want to create a knowledge graph based on the Neo4j Wikipedia page. So we would gather the text from the page. So Neo4j is a graph database management system, blah, 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 blah. Right. We would split that text into chunks to make it more manageable to deal with. We would then create embeddings and vectors for each one of those chunks. And then finally, we would take that, those pieces of text, those chunks of text, pass them to an LLM and ask the LLM or instruct the LLM to say, can you identify entities and relationships within this text and give me back a JSON, a piece of JSON data. So we do that and we get back some JSON, and we can then use that JSON to generate the graph. So create cipher statements to actually generate the graph. So based on that Wikipedia page, we could generate a graph that says Neo4j, the graph database, was developed by Neo4j Inc., the company. Neo4j, the graph database, is implemented in Java, which is a programming language. So based on that unstructured data, we have been able to generate a knowledge graph that describes the content of that text. So that's the process that we are going to go through. All right, so let's go to our first practical exercise. What we are going to look to do is to generate a schema based on some text. So we're going to use the GraphRAG for Python package. It allows us to access the Neo4j GenAI functions. And we're going to use this package to build the knowledge graphs and create retrievers. But in this session, we're just going to, lesson, we're just going to look at how we can extract a schema from some text. All right. So the first thing we're going to do is we are going to open up this file, workshop GenAI extract schema. And this code is, I'll just show it. So it's workshop GenAI extract schema. So this is the first program that we are going to look to write. And what this code does is first of all, it creates this object schema from text extractor. That is part of the Neo4j GraphRAG package. We need to give it an LLM. So the LLM's job is going to be able to turn the text that we give it into a schema. And we're going to tell it to use structured output. So this is the text that we want to turn into a graph schema. Neo4j is a graph database management system developed by Neo4j Incorporated. And then we're going to run it. So let's give it a run. So when we run it, it's going to take that text, generate a prompt that instructs the LLM to generate a schema, and then finally it's going to give us the results back. Hopefully. Here we go. Brilliant. Oh, there we go. Excellent. Just took a little while to come back. So we can see back that we have a document structure that represents a graph schema. We can see that there is no type of product, no type of company, and that there are also relationships types between our schema. So we can see that the product was developed by the company. And if we go back to, sorry, I've lost the page that I'm on. Where is Graph Academy gone? Oh, here it is. So yeah, we get back something that looks like this, and we can see that it's generated a schema that allows us to understand that the graph database was developed by this company. Now there are a couple of further examples that you can try. So just try different pieces of text. So copy the text out, replace the text here, and just explore and just understand actually how can we turn text into a graph schema. So I see I'm getting an error when running the failed test. So the test is telling you that the environment file doesn't exist. .env file not found. Typically, what I find with people is that when I've run this before, so you have to create a new file called .env. What a lot of people do is update the example instead. If you have done that, just create a new file called .env. and put the information into there, or just check that this file is called .env and that it's in the root of the folder as well, so it's not in one of these other folders. I will do my best to zoom a little bit. I'm sort of starting to run out of room. I will do my very best to kind of keep things as readable as they can be. So you asked a question. The DMV example file does not contain the credentials for Neo4j. No, it is. So if you go to Graph Academy, it is here on this GraphRAG for Python lesson. There is this. These are your credentials. So this is the instance that was created for you. Okay. Right. So spent some time extracting some schema from text. I ran this example here. So Python's a programming language created by Ida van Rossum. And yeah, so when I ran this for this text, we can see that there is a no type of person, a no type of programming language, and that the programming language was created by the person. So we can see how we can create a schema based on text. Okay, so let's move on. So we're going to move on to our next section, which is creating a graph. So we are actually going to create our graph now. So again, the Neo4j GraphRAG package includes a class called the simple KG pipeline. I don't like the fact that it's called simple. Simple suggests that you can only do simple things with it. That is not true. You can do you can do advanced things with it. It is just simple to use. Right, that's its idea. But we're going to use that pipeline to do those 5 steps that we talked about: loading text, splitting text, creating embeddings, extracting entities, and writing data to our database. Okay. So this is what we're going to do. And if we look at the pipeline steps, so this simple KG pipeline, loads documents, splits them, embeds them, entity and relationship extractor, pruner, so getting rid of things, maybe duplicates, a writer, and then a resolver. So that's the process. That is the pipeline that our simple KG pipeline is going to deliver for us. So our task, the thing that we are going to do is we want to create a knowledge graph from unstructured data. So we are going to take lesson content from Graph Academy. In this case, it happens to be lesson content from a course of ours called Neo4j and Generative AI Fundamentals. We're going to take that unstructured data, so text, and we're going to look to create a knowledge graph using this simple KG pipeline. So your task is to open up this file, this KG builder file. I want you to review the code and look at actually how does that simple KG pipeline work. Then I want you to run it to create a graph. And then I want you to review the graph. I will go through the same process as well. But before I do that, I'm just going to take a moment just to kind of look at any questions that may have come in. But yeah, all of the information you need is in front of you. So it's here. We're going to create a knowledge graph. This is your task, and all of the instructions are there for you to follow. Okay. I just have a quick look at Q&A. Iman, could you explain more about schema? Should we define that in advance before running text through it? Iman, we are going to. You do not have to explain the schema before running it. We are going to go through the process of running it without a schema and then also defining a schema as well. So we will cover that within the session as well. And then. Okay, I think we're good. Right. Alex always needs a call out. Thank you, Alex, for answering questions and dealing with the chat in the background. Yeah, so I'm going to go through this process as well. Workshop GenAI knowledge graph builder. So this is the program that we are going to look at. So we'll have a run through. Run through this code before we run it. So this will start to look familiar to you because most of the exercises we're going to do are going to do things like we're going to create a connection. That's what this code does. It uses the graph database driver to create a connection, passing in the information that we put in our environment file. So we're going to create a connection to Neo4j. We're going to create an LLM. So in this case, we're going to use OpenAI's GPT-4 Nano, and we're going to put the reasoning effort to minimum. So we need an LLM. We need an embedder. So embedder is going to turn our text into embeddings and vectors. And then finally, we need to set up our simple KG pipeline. So in order for our pipeline to work, the minimum things it needs is it needs to know which LLM it's using, which connection it's using, what embedder it's using. And in this case, the data that we are going to load is actually PDF documents. And then finally, we're going to run it. So we say, well, what's the PDF file we're going to run? And then we run that file. And then finally, we print the result. So if we can have a look at this data is in this repository. So if we look in the data folder, we'll see that these are all the PDF files that we are going to use to generate our knowledge graph. And if we look at the first one, we can see generative AI. This is the unstructured data. This is the PDF document that we are going to use to generate our knowledge graph. And it happens to be the first lesson in that Graph Academy course. Oh, I've lost my KG Builder program. Here it is. All right. So I'm going to run it. Let's give it a run. So what it's going to do is we're going to run it. It's going to open up that PDF document we just had a look at. It's going to go through those processes of loading, chunking, embedding, doing entity extraction, and then creating our graph. And there we go. Okay, so not great result. I only got one there. I got one node out. Let's have a look and see what happened. But if we go back to our lesson content, so the pipeline creates a graph model that looks like this. So we have documents, we have chunks, and we have entities. The entities are from the chunks. So the entity nodes represent the things that it found within the document. So we can have a look at the documents that it's created within our graph. So if I run this cipher statement, what we can see is this is the path, this is the document that it just processed, and this is the text that it took from that document. So we can see that all of the text was created from that document. Now, at the moment, I've only got one row. I've only got one chunk for the one document that's been created. And that's because at the moment, the default chunk size is actually larger than the length of the document, right? But that's one of the things that we are going to change. We're going to look to change that and chunk it, chunk the document and see what the result of doing that is. And then finally, we can have a look at the entities. Now, when I ran this, I only got one entity extracted. I suspect it's because my my chunk size is quite large. And again, we're going to look to change that. So if we just have a quick look at, it found one entity in that, which was generative AI. We're going to do a better job. We're going to tailor, we're going to change the process to change the chunk size and also look to define a schema. So we should get more data out. One thing to note with all generative AI applications, this is non-deterministic, right? Your results could be different to mine. Yeah. Okay. Let's have, while you are taking a moment just to go through that, I'm just going to have a quick look at see if there's any questions. So Q&A. Just curious why models are different for LLM and embedder. So the reason the models are different for LLM and embedder is because they are different models. So we typically, so this is a GPT, a transformer model, a large language model. This is a text embedding model. They are different things with different purposes. Kev also asking, I got an error, unexpected keyword reasoning effort. Is that so? I would not expect you to get that error if you are using this model, GPT-5 Nano. This is how you set the reasoning effort. We set the reasoning effort to low to do or I've set it to low for this workshop, mainly for speed. The lower the reasoning effort, the quicker the model returns, and actually for the purposes of the data that we're looking at, minimal reasoning effort is fine. Okay. I keep losing my place. Yeah. But yeah, if I expand the nodes from our generative AI entity, this is the entity that the LLM extracted, we can see that it's from this chunk, and we can see that this chunk is from that document. We're going to spend the next couple of lessons improving this process to create a graph that is more specific to our needs as well. But yeah, you should get to the point where the simple KG builder runs and returns some data and at least creates a graph. Okay, so I'm going to move on to this next lesson here, which is chunk size. So, as I said before, the graph created by the KG pipeline is based on the chunks of data that are extracted from the documents. The chunk size is quite large by default, which chunk size is a matter of kind of strategy, and I truly believe there's an element of experimentation in there in terms of understanding your data. But by and large, the larger the chunk size, the more context the LLM has, but it may lead to less granular data, as I have just seen in my example. I only got one extracted entity. But obviously, the smaller the chunk size, the more granular it may become, right? But we are going to look to change the chunk size, and we're also going to look to change the schema to look to gain more specific information. But there is an element of experimentation, and also chunking strategy. Size may not always be the right thing. You may look to chunk by sections or by some other kind of parameter. So this is your task. You are going to delete the existing graph, create a fixed size splitter. You're going to modify that pipeline. You're going to run the pipeline, and then you're going to look and see what impact it has. Again, all of the information is here. So there's instructions here to delete the graph. We're going to recreate it, creating that fixed size splitter, updating the pipeline, and then exploring. I will go through the process as well, but I'll just take a moment to kind of look at any questions as well. Harshil, just curious to know what makes chunking produce non-deterministic results. Usually non-deterministic rise from the grounding step. Harshil, maybe I didn't explain. I'm saying what you're saying, which is the non-deterministic part is the entity and relationship extraction done by the LLM. As we change the chunk size, typically the smaller the chunk, or the more specific we are about the schema, the more information we get out. Yeah, but yeah, we're saying the same thing. Are the embeddings model specific? Would we re-embed the full graph if we change the embedding model? Are the embeddings model specific? Would we re-embed if we change the embedding model? Yeah, so we will look at embeddings in vectors, but you do not have to. Yeah, but the way that we query a vector, we do so using the same embedding model as the data was embedded with. But we will go through that process as well. Okay. All right. So I'm going to look to modify the chunk size and kind of go through that process. So first of all, I'm going to be re-importing all of this data and modifying this existing graph. So what I'm going to do is I'm actually just going to delete everything. So this modify match end detach delete end basically matches all of the nodes and then deletes them. So let's look at modifying this chunk size. So I'm going to need first of all, I'm going to need this fixed size splitter. So what this fixed size splitter does is, as it says, it splits chunks based on a particular size. So I'm going to modify my KG builder, and I'm going to create my fixed size splitter. It doesn't actually matter where I create it, but I'm going to create it just after my embedder. So here's my fixed size splitter. I want my chunks to be about 500 characters, and I want an overlap of 100. So essentially what that means is chunks will be about 500 characters, but the 100 characters from the previous chunk will be in the next chunk. Once I've done that, I can update my KG pipeline to use that fixed size splitter. So here's my KG builder. What I'm going to do is say, okay, we'll use a text splitter. This is the text splitter I've created. When you run the pipeline, use this text splitter. And that's all the change that I need to make. If I now run my program again, sometimes I wonder whether I press run then. Run my program again. It's going to take that PDF document, load it. It's going to chunk it based on this chunk size here, and it's going to run it through that entity and relationship extraction process to create my graph. Now, it's an interesting thing that has happened. So the feedback that we get is the number of nodes to resolve and the number of nodes created. So by changing the chunk size to be smaller, I got considerably more data out than I did when I just ran the pipeline to start with. So let's have a look at the new graph that we have created. So, like, first of all, if we have a look, we can see that. So this query finds the documents and finds the chunks for those documents. So we have our path and we have each of our chunks. So now we can see that for this one document that we now have 8 different chunks. Yeah. And if we have a look at the entities for each of these chunks, so this is the entities that have been extracted from this text document. Now, as we saw the last time that I ran this, I actually got one entity out, which was GenAI. Now, just through changing my chunk size, I now get considerably more information. So I can see from this chunk here that generative AI concepts are trained on LLM models. And I can see that LLM generates generative AI trained on LLMs. So we can start to see that we are getting information out that is more relevant to the information. And we're also starting to see how chunks are related to each other. So there are 3 chunks here that all reference generative AI. So just by changing the chunk size, we can see that we can significantly influence or change the data that we get out. Okie dokie. So have a moment. I'm just going to look at some questions. Paco, sorry I missed. When the LLM extracts the nodes and relationships, does it use the whole text or does it do it for each chunk? It does it for each chunk. And that's why changing the chunk size can have such a significant effect on the output that we get. Okay. All right. And if we start to look at if we start to look at the properties for these nodes as well, so this node here happens to be a chunk node. We can see that it has a few properties. First of all, it has the index, so that's where it appears within. And if we open up where it appears in this document, so this is from this document. So index number 3, it's the 3rd chunk. So we can see the text, and we can also see the embedding. So this is the embedding. This is the vector that was created by our embedding model, and we will use that throughout the workshop when we move into creating retrievers. Okay, so where we are up to now is we have taken some unstructured data. In this case, it's a PDF document. We have extracted entities from it, and we have changed the chunk size. And by changing the chunk size, we've found that we can extract more relevant information. So let's move on to defining a schema. So the knowledge graph that we just created it's unconstrained, and so that any entity or relationship that could be created based on the text, the LLM is just going to look for whatever it thinks is right. Yeah. But this can lead to our graph being like non-specific, difficult to analyze, and this we've kind of seen with the test that we've been doing, sort of like, oh, okay, well, it talks about GenAI quite a lot, but actually is that actually the thing that we're interested in within that text document? So what we're going to do in this lesson is we're going to look to modify it to define a schema. So we can provide a schema that allows us to instruct the LLM to say, what are the things that we are interested in? So we may be interested in people, organizations, locations, the following relationships, works that located in, and the following patterns. So we're going to look to define the things that we are interested within our unstructured data, and this allows us to build a much more specific graph. So again, your task is there is a new program to write, and there's a kind of pattern to these exercises. I provide some starter code. In this case, it's this KG builder schema program. Review the code. Then I want you to define a set of nodes, relationships, and patterns that are relevant to that data. Then modify it, then run it, and then iterate on that and say, actually, how does modifying the schema change the information that we get out? And we can continue. Like I said, I will go through the same process, but again, all of the information is here, starting from opening up this program and going through the steps to modify the schema. What I will do, press the right button, is just have a quick look at any questions. So Paco asked a question. I think it's on the basis of the question asked before. Then how does it work out how to link chunks together? So it links. So the graph describes how chunks are linked. So if I say, for example, so match, there is only one document. So this is the document that we have in the graph. We'll make this a bit bigger. So this is that one document that we have in the graph, and the relationships from this document node, have all of the chunks that were extracted from it. So we could write a query that says from document, and let's get the chunks out. So we can say the chunk dot, I think it's path, yeah. So let's say we want the path of the document, and then the chunk text. So now I get back these are all of the chunks from that document, and I could go further and say order by c.index, by c.index, and then I get back an ordered list of all of the chunks within that document. So our graph tells us, our graph describes how those chunks are linked together. Best Paul, you ask an interesting question. When passing the data to an LLM, how do we prevent hallucination on the part of the LLM in creating nodes? In the same way that we do for any request, we provide good context and good information. providing a schema, the activity that we are going through now, is by and large the best way of getting out the data that you want without the LLM making stuff up. But it's down to the same processes that you would use for avoiding hallucinations. So good prompts, good context, right? We won't go through it in this session, but you can modify the prompts that the simple KG pipeline uses as well. Okay, I'm going to go through the same process of creating a schema for my knowledge graph builder pipeline. So I've just opened up this KG builder schema. Now you'll see that the first thing that's been added to this is these nodes. So these node types describe the things that I'm looking for. In this case, technologies, concepts, examples, and processes. And I can simply pass them to the KG pipeline. And it will go through the process of creating a graph, but only looking for those 4 things. I will just very quickly run that. One of the things I need to do is, let's just delete everything in my graph again. And then I'll go through the process of rerunning it. And what I want is I just want these node types out. Yeah, give it a run. It'll take a moment to run. And again, what it's going to do is it's going to use this data. So use these node types to find the nodes within the text. So I'm only interested in technologies, concepts, examples, and processes. Again, this data is it's a lesson, right? Those are the things that I'm interested in. So it's just finished. And again, interestingly, one of the things we noticed is that I now get more nodes out than I did when I left it as unconstrained. When I left it as unconstrained, I got all sorts of things out. But now I get a much more defined schema. So if I run this query to say, this query basically says find all of the entities from the chunks and say how are those entities related. So in this case, I've got the generative AI, it's a technology, knows large language models, the concept, limitations of LLMs, there's a relationship to access to data. So kind of so on and so forth. We can start to see how by constraining the data, we get out the things that we are interested in. So the process of lesson, knows hallucination and information. Now we can define more than just nodes. We can also define relationship types and also patterns as well. What I'm going to do is I'm going to go through the process of defining a set of nodes. So in this case, I want technologies, concepts, examples, processes, challenges, benefits. I'm also going to say, okay, well, I actually want resources as well. Now, these are node types that I'm interested in, but I can be more specific and say, actually, well, I want to find resources, but actually I want to give you a description of what that resource is as well. So going back to Paul's question, you said, well, how can I reduce hallucination? The better the context that you provide in terms of I'm looking for resources. In this case, I define a resource as a learning resource such as a book, article, video, etc., and also define the properties that I want as well. So I can be much more specific about the information that I am looking for. Better context leads to better better outcomes. So I'm just going to. So here is my complete program that's got all of the node types I'm interested in, all of the relationship types I'm interested in, but also the patterns as well. So the things I'm interested in is how technologies are related to other technologies, how concepts are related to technologies, so on and so forth. Where technologies have challenges, where processes leads to benefits, so on and so forth, right? But we can define and be as specific as we need to be to describe the data that we have. Again, I'm just going to delete all of the data. I'm just going to run this process again with that kind of specific graph. While that's running, does embeddings help in reducing hallucinations by any way? Not in knowledge graph construction. No. Again, so I've run my process, and again, by being more specific about the things that I'm interested in, I'm actually getting a more consistent knowledge graph out. And again, so if I look at how entities are related to each other, we can see that the concept of generative AI is related to the technologies of large language models. We can see that the technology of text generating models is related to large language models. So we're starting to see a graph that makes sense. So, a simple question is used in the technology of prompt. The concept of intent is related to the technology of a prompt. What's this one? Descriptive processes are part of prompts. There you go. So we're starting to describe the data and the information that we are looking for. So I just give you a moment to explore, ask questions, ask a question. If we need to have different types of nodes, so we should define separate schema for each node type. I think there's an element in terms of experimentation. So if we look at this example here, for these node types, I've basically just said, technologies, concepts, example, processes, challenges, benefits. I kind of like deem them to be self-explanatory, but based on your use case, you may want to be more prescriptive about what they are, as I have done here. Okay. Right. So we have defined a schema. The last step that we are going to do in this kind of knowledge graph construction piece is we are going to add some structured data to our knowledge graph. So the knowledge graph that we have created is solely based on that unstructured data extracted from documents. Now, it's likely, to be honest, that you'll have access to structured data as well, whether that's databases, CSV files, APIs, whatever. And combining our structured and unstructured data can enhance our knowledge graph's richness and usefulness. So, in the repo that we are working with, there is a sample CSV file that contains metadata about the documents that we have been creating our knowledge graph from. And actually, if we just have a look at it, it's this document here. And it's basically a knowledge graph about, well, for each file name, we have what course it's from, what module it's from, what lesson it is, and also what its URL is. So we have some metadata, some structured data about our documents. And we can use this CSV file as input and as a structured data source when we create our graph. So we are going to look to create this structure. Now, so the document chunk entity structure already exists, right? What we are going to look to do is add lessons. So this is our structured data. It's structured data about each lesson that this document is part of. So this document is a PDF of this lesson, and this lesson is going to contain information like what its name is, what module it's from, what course it's from, and also its URL, like how to get to that information. So your task is to, again, similar process. We're going to open up some starter code. We're going to have a look at how that does it. We're going to run the code, and then we're going to review the graph and the structured data that it creates. And again, I will go through the process as well. And before I do that, I will just have a quick moment just to look through any questions. So just to kind of recap where we are doing this task here, which is adding structured data to the knowledge graph. Here's our starter code, and here are the instructions for you to follow along. In fact, what I would do, I'm just going to tidy up because I feel like I've got so many things open. So here is the starter program. Here's our connection to our database. Here's our LLM. Here's our embedder. Here's our text splitter. Here's our schema information that we just created. Here's our pipeline that includes, our splitter and our schema. What we are going to do now is we are going to open up our CSV file. So that's the CSV file that's got all of that structured data in it. And we're going to define a cipher statement. So it's this cipher statement that's going to add the structured data to the graph. So we can see it matches the document. It merges a lesson node in, sets some properties, and then creates that relationship as well. So match document is a PDF of this lesson. And what this is going to do is it's going to go through every document in this CSV file. So it's going to go through every single one of these documents. It's going to run the KG pipeline. So it's going to run the knowledge graph extraction. And then it's going to run that cipher statement to create the structured graph as well. Now this is going to do every single document. So I'm just going to run it and I'm going to let it go while I look through any questions and talk about anything else. So picked up the first document and it's going to process the first one. And like I said, it's going to go through every single one of these documents and it's going to essentially create a knowledge graph of the contents of all of these documents. So we'll see that as it runs, in fact, we're now on document number 2. It's going to kind of run through and go through that process. Right, let's have a quick look. I'm just going to quickly go back through and just kind of make sure that there's if there's any questions that I have not answered. Add a question: would it be possible to run the course later? Absolutely. This content is yours. You can go through it at your own pace if you want to. Yeah, it's available for you to use indefinitely. Yeah, it's not going anywhere. I should ask put something in the chat. Oh, it's gone. Oh, it's been moved. It's been moved to a question. What is the best way to retrieve domain data stored in relational data? Generate runtime SQL to graph, or generate entire DB into knowledge graph before grounding? I mean, with all of these questions, right? It depends. It depends on your use case. My opinion would be if you have structured data, that you can create a structured knowledge graph from, you don't need to use an LLM, right? Go through the process of understanding your structured data, defining a graph data model, and building a pipeline to essentially import your data into your graph. So say if you have highly structured data, I don't think you need to use an LLM. If you have unstructured data, use an LLM. Where you have mixed, use the best choice of those two technologies. I just kind of quickly go back. So yeah, it's currently, I think I'm nearly finished. So it's going through and it's created. So I think it's now on document. Oh, it's on the last document and we're done. Right. Okay. Brilliant. So if I just expand, so this is me running it. We can see it's gone through every single document. It's resolved however many nodes from each document. Now we have a complete document in our graph. Now, so the structured data is going to allow us to query this graph in new ways. So if we have a quick look at this cipher statement, essentially what it says is like match. I want you to find a technology node that contains the name knowledge graph. So it's looking for any entity node, anything. Oh, what happened there? Any entity node that was extracted from the documents. And then what it says is, okay, well, find any node that contains the word knowledge graph, find the chunk, find the document, and then find the lesson. And then return the name of the technology node, the name of the lesson, and the URL of the lesson. So if I run this, what we can see is, okay, well, there are technology nodes within our graph, and they link to specific lessons. So now what I can find is I can find all of the lessons that cover a particular technology or concept. So let's just spend some time and explore this graph. So if I say match. So this will find return a limit 100. Yeah, something like that. So this is the first 100 entities that were extracted from the graph. So there is a concept around transparency that has been extracted from this document. If we expand the relationships from this, we can see that actually transparency was extracted from this chunk, which which is part of, there'll be this document, and this document relates to this lesson. Yeah, this lesson on LLM fundamentals. So our graph has become significantly more useful, and we can start to see how things like, so there's a technology called temperature control that's been extracted from our lesson text. We can also see that there is a resource called a Reuters article and a link to a Reuters article which cites the technology temperature. Temperature control leads to the benefit of consistency and precision. So what we have found is that by expanding our graph to include our structured data, but also to include much more data, our graph has become much more complete and describes things, describes the things that we are interested in. So I just picked another one. There is an entity called concept of transparency that is related to the technology of GenAI models. And we can see how all of these concepts are related to the content that we have extracted from them. I'll just have a quick look. Let's just go back to this query as well. So let's say rather than knowledge graph, we're looking for hallucination. So let's find lessons that are related to hallucinations, of which there is one. And it is a lesson on generative AI and considerations. Okay. We have this knowledge graph now that consists of all of these entities that we extracted from our documents, and also this structured data that we got from our lessons. So we can do things like this. So we can say, okay, well, if we start with the lesson and we find the documents and we find the chunks, if we return the lesson name and the lesson's URL, from each of the chunks within the lessons, let's go off and find all of the documents, all of the technologies that relate to that lesson, and all of the concepts that relate to that lesson. So it allows us to look at our graph in different ways. So we have lesson, what is generative AI? And we can see that it references technologies, generative AI model, GenAI, large language models, prompt. Perhaps we need to think about how we do our entity resolution, because they are definitely the same thing. So on and so forth. But yeah, so we can start to see things like information extraction, prompting, and we go into different lessons now, so we're starting to see the same concepts repeated. But yeah, so how we can use our structured data and our knowledge graph allows us to look at our information in different ways. Okay. All right. What we're going to look to do now is, there is an activity here, and I would encourage you to do it. So it's actually the last activity, create your own knowledge graph. I'd encourage you to have a go. The code that we have used. So this is, it's just over 100 lines of code, and I've spaced it out pretty well to make it more readable. So this code is all the code you need to generate a knowledge graph. And I would encourage you to have a go. Right. So find a set of documents. Maybe you have a set of documents, and create that knowledge graph and spend some time iterating on it. Because what you'll find is, by changing the schema, changing your chunking strategy, you can start to answer questions about your unstructured data that you couldn't do before. So yeah, I'd highly encourage you to come back to it and have a go at this kind of optional task of creating your own knowledge graph. But what we are going to do is we are going to move on to retrieval. Oops. do apologize. So we are on this third module here, retrieval. So what we're going to look in this module is we're going to look at how we can use our knowledge graph, how we can retrieve information using vectors, vector plus cipher, and text to cipher retrievers. And we're going to put those into GraphRAG pipelines as well and see how we can use our knowledge graph to answer questions about our data. Okay, so we previously spoke about RAG, or Retrieval-Augmented Generation, and the role of retrievers in finding relevant information. Now, one of the significant challenges of RAG is understanding what the user is asking for and finding the correct information. Essentially, what we're looking to do here is to find enough information that enough information and context to give to the LLM that's going to allow it to answer that question correctly, but not too much that it confuses it, right? And that's why I spoke about the role of retrievers being super important. So we're going to look at semantic search and how vector indexes can help us find this relevant information. Again, let's define some terms. Let's talk about some concepts. So when I talk about semantic search, what I'm talking about is finding information based on intent and context meaning rather than things like individual keywords. So, like, for example, like if I was to search for apple, I might expect to get results about fruit, right? However, in semantic search, what I'm looking to do is say, okay, well, what is the context of the question being asked? Are you looking to search about fruit, the tech company, or something else? And the results that we get back from a semantic search are based on the term and the perceived intent. That is the thing that is important when we're doing semantic search. And vectors allow us to perform semantic search. So when I, again, talk about vectors are simply a list of numbers, right? And we can use vectors to represent data. So in this example, we can use three numbers, a list of three numbers, a vector of three, to represent a three-dimensional point in space. Yeah. Now, the higher the number of numbers, yeah, the dimensionality, right, the more fine-grained meaning we can have, but also the more expensive it is. So we have semantic search. Vectors support us in being able to do semantic search, and they do that through embeddings. So when we talk about embeddings, we are essentially talking about vectors in the context of machine learning and NLP, right? And embeddings, the word embedding is typically used for a vector that has a specific purpose. So we could create embeddings that allow us to do semantic search and store them as vectors. So if we have, so when we have multiple dimensions, so multiple numbers within our vector, and we use a semantic search model to create an embedding, we could have dimensions for things like fruit, technology, color, taste, shape, right? The different dimensions allow us to describe different concepts or attributes or meaning behind that word or that phrase, right? The most common method of creating an embedding is using an embedding model, which is what we have been doing when we built our knowledge graph. And it's much more common, as we have been doing, is when we create embeddings for entire sentences or paragraphs, yeah, or complete documents maybe, yeah. And it's important because by creating an embedding around, a sentence, a chunk, a paragraph, yeah, we gain more contextual meaning about what that text represents. All right. So we have some text. We use an embedding model to create a vector from it. Like, how do we compare that to other things? Well, the simple answer is you look at the distance or the angle. So if we have a vector for the word apple and a vector for the word fruit, right? If we compare the distance between those two vectors, which is sort of easy to imagine in three-dimensional space. It gets much more difficult in dimensions further than that. If we look at the distance, the closer they are together, the more similar they are. The further apart they are, the less similar they are. And we can use semantic search in vector-based RAG to find these contextually relevant results for a user's question. So an embedding model is used to create an embedding of our source data. In this case, we used an embedding model to create an embedding of our chunks, and we stored that in a vector index. So when we use RAG, and we use semantic search as part of RAG, the process looks like this. User asks a question, a prompt. Our application takes the question that they asked, creates an embedding of the question, so uses the same embedding model to create a vector of the question, compares the question against all of the embeddings from our source data using that vector index, returns those as results, and gives those results to our LLM as that enhanced prompt. So that is the process, right? We take our source data, we use an embedding model to create vectors. We take our question, use the same embedding model to create a vector of the question, compare the question to all of the source data, and that allows us to pull back the most similar results based on that information. Okay. So that is vectors, that is semantic search, that is vector-based RAG. What we are going to do now is we are going to build a vector plus cipher retriever. So the chunks in our knowledge graph include vector embeddings. We saw them when we had a look at each chunk. We could see that there was a property against each chunk node, which was the embedding. So what we're going to do is we are going to create a vector retriever that uses these embeddings to find the most relevant chunks for a given query. And our retriever is going to use that structured and that unstructured data in our knowledge graph to provide additional context. All right. So while we have chunk nodes and we have embeddings on those chunk nodes, so at the moment we don't have a way of querying them because we haven't created a vector index. So if we just do return, let's just have a quick look, limit 10. So these are the first 10 nodes. We can see that each chunk node has some text and an embedding. What we're going to do is we're going to create a vector index that's going to allow us to do vector search against those embedding properties. So we're just going to run it, right? No data present. It ran the query. It didn't return anything, but yeah, the index has been created. Now, if we look at this, we can see that the number of dimensions we've got is 1,536. That is the number of dimensions that is returned by the text embedding 3 small embedding model, which was the embedding model that we used when we created our knowledge graph. And if we look at our code, this is the code that I ran to create the knowledge graph. That's our embedding model. So we're going to use the same number of embeddings in our vector index. All right. Now we can actually search that vector index. We can search those embeddings just using Cypher. So if we have a look at this this Cypher query, what this does is it says, okay, well, create an embedding model. This is a Cypher function. Create an embedding model for this phrase using OpenAI with this embedding model. And it's going to create a user embedding. It's going to create an embedding for the term Retrieval-Augmented Generation. Then it's going to search the chunks, and it's going to search that vector index we just created with the embedding we just created, and then return the chunk text and the score. So I am just going to run this. It's going to fail to start with, because what I need to do is I need to put our OpenAI token in there, which is this big fella here. So put this in here because I need to provide it with an API token in order to be able to run it. But when I run this, what I get back is, so this is what's been returned, the chunks that we found and the score. What we get back is the chunk, the text from the chunk and the score. So I asked it to search for retrieval-augmented generation, and the first chunk that I got back, boy, is lesson content about the retrieval-augmented generation process. And it also gives me a score. And it's a score out of between 0 and 1, closer to 1 being the more similar those two things are. Yeah, so we can use Cypher to actually query our vector index, and we can see that process of creating a vector for our question and then using the vector index to find the most similar results. So again, you have a task to do. Again, it's the same process we've seen before. I've provided some starter code. Your job is to review, run, change, iterate, so on and so forth. Again, I will go through the same process, but I'll just take a moment to look at questions as well. So just to recap where we are in this retrieval module here, and we're on vector plus Cypher retriever. And again, the instructions are here. So here's your task, and here are the broken down instructions for you to run through that process. Again, I will do it. I'll just have a look at questions first. So Sean asks a question. So at scale, does it make sense to continue to have the chunks in nodes, or are they better optimized as property data, or is chunk nodes an optimal approach at scale in your experience? It's like so many of these questions, particularly ones about how to model your data, as it depends on your data. I would say having chunks as nodes is the right approach. Using a node label is a fantastic way of segmenting your graph, and it's an incredibly cheap and efficient way of storing data within a graph database. Particularly if you want to say, like, show me all the chunks, that's going to be incredibly quick. By and large, when using graph databases in Neo4j, finding nodes and traversing relationships is incredibly cheap. Pulling data back from properties is more expensive. PacoS question: similarity score is based in Euclidean or cosine distance. It is up to you. When you create the vector indexes I did here, we define a similarity function. So it's up to you. I have used cosine, but yeah, you could use Euclidean if that fulfills your use case better. All right. So yeah, like I say, I will go through the process as well of creating this vector index. Where are we? We are here. So again, I'm just going to have a bit of a tidy up. We've got all sorts of things open. So we're starting with this vector Cypher RAG program. And if we just have a look at this code, again, we can see things that look familiar. We have a connection to our graph database. We have an embedder, and we have a retrieval query, and we have a retriever. All right, so these embedder, that's fine. We need an embedding model because we need to turn our question into an embedding. Our retrieval query is what is pulled back from the graph after we have done our vector search. So in this case, it's just the node text, so the text of the chunk and the score. We define our retriever. When we define our retriever, we tell it what we're connecting to, what index we're using, what embedder we're using, and also what data we want to pull back afterwards. We're going to define an LLM. One of the things we're going to do is we're going to define our LLM because we're going to create this GraphRAG pipeline. So our GraphRAG pipeline is going to take a question, right? So what is a knowledge graph and where can I learn more about them? It's going to take a question. It's going to use our retriever to find information based on this question, and it's going to use the LLM to define a response. So once we've created our RAG retriever, we pass our query, we run it basically. We run it, we tell it, okay, well, I want the top K, so the number, how many results do I want back? When I do my vector search, give me the first 5. And I'm also saying return the context as well. So the context is what's the LLM used in order to generate this response. But yeah, if I give that a run, what we should see is I get again, it's a little bit difficult to see, but what we have here is, based on my question of what is a knowledge graph and where can I learn about them, a knowledge graph is an organized representation of real-world entities, like things, people, places, food, and relationships between them, so on and so forth. And it's also giving me to learn more. You can see this blog post as well. Okay, so that seems like a completely relevant response to the information that I gave it. Let's just go a step further and say, okay, well, you know what? Let's prove that, right? So what I want to do is we can actually print the context. We can print the context that was used by our GraphRAG pipeline. So here is the code where I print the response, the answer. What I'm also going to say is actually print the context as well. So I'm just going to give that a run. I've also noticed I'm using a deprecated function now, so I need to fix our workshop, which I will do in due course. So now we get back. So we get the same response back. This is what a knowledge graph is. You can learn more. And actually, if we look at the context, so the context is, what did our retriever return? It's a little bit difficult to read, but we can see we get a record item of what is a knowledge graph. And we also get additional information. You can learn more about the blog post. So we can see how this context, the context from our knowledge graph, was instrumental in driving what the response was, which is this bit here. A knowledge graph is an organization representation. And you can find more information from our graph. So we can see from our context that that the data was used in order to generate that response. Okay, now when we defined our retrieval query, which is this information here, is really simple. It basically says just return back the chunk text and the score. We can make that much more sophisticated, and that's where GraphRAG comes into RAG. So we can use our graph, our knowledge graph that we've created, to find additional context that we can give to our LLM. So what I'm going to do is I'm actually going to update this retrieval query so to be something more sophisticated. So now, rather than just returning the chunk text and the score, I'm going to return, well, the chunk text and the score, also the lesson URL, and also I'm going to return what technologies are referred to in each of these lessons, and also what concepts are referred to in each of these lessons as well. And my expectation is if I give it better context, I will get a better response. Again, it's a little bit difficult to read, right? So what I get back now is a knowledge graph is, again, I get a similar response back. I get a similar description of what a knowledge graph is. But actually what I also get back is, based on the additional information within my context, which included the lesson URL, I get, well, you can learn more here. You can actually learn more in the lesson where this information came from, as well as the blog post that was referenced before. We can also see that context, their attributes evolved over time. It's going to be difficult to kind of pull this text out because there's so much information. The bit that I'm looking for is this bit. Yeah, how they relate, supporting a holistic view of information, enabling complex queries, analytics and insights. That is information that has come from our knowledge graph rather than direct from the text itself. And there are some additional things that we can try. We can make an even more sophisticated retrieval system. So we can also do what's called generalized entity retrieval. So if I run this query, what this query does is it returns all of the entities that are related to those chunks. So we can see that concepts. There is a concept that's generative AI is related to the technology GenAI. This is all information that has been generated within our knowledge graph from the unstructured data. So, let's just have another go. Let's create an even more sophisticated retrieval query. An even more sophisticated retrieval query, which uses that information and uses a knowledge graph to generate this idea of how are entities related to each other. And if we look at these, we can see that they are essentially, facts. So the concept of generative AI is related to the technology of large language models. They're essentially generated facts from our unstructured data. And we've got some examples here we can use. So let's experiment. Let's change our query to be what is hallucination and how can I avoid it? So again, it's going to use our knowledge graph. It's going to use that information to generate a response. Hallucination is when GenAI and LLM generates information that sounds plausible but is misleading or basis. You can reduce hallucination by providing context using retrieval-augmented generation, keeping in mind model limitations. Yeah, again, it's information that we can see from our context. And going back to what we saw before, for example, answering the moon is made of cheese. Again, that is information that's taken directly from our knowledge graph rather than its training data. Yeah. Okay, so the very last thing I want to talk about is the last lesson in this retrieval module, which is about text decipher. So we are going to create a text decipher retriever, and it allows us to create GraphRAG pipelines to answer natural language questions. And it does this by generating, executing cipher queries directly against our knowledge graph. Text decipher is super useful if you want to get precise information based on users' questions. So things like how many, what is, tell me about. Right? And we're going to create this text decipher retriever and use it to answer questions about data in our knowledge graph. So again, there is a task for you to do, which is there is some starter code, review it, run it, modify it. I'm sure you've got used to this pattern as well. Again, I'll take a moment to look at any questions, and then I will go through the same process as well. Oh, we have no questions. Right, I don't think there's anything that I haven't covered. Okay, brilliant. Okay, excellent. I will go through the process then of looking at this text decipher query. All right, so we start with this program here, which is our text decipher RAG. Again, I'm sure it's looking familiar. So we have a connection to our database. We have an LLM. Now, one of the things that we can do with our text decipher retriever, and it's a great thing to do in terms of helping generate good cipher statements, is providing it with examples. So in this case, if a user inputs find a node by name, use this type of query. And if we look at the query, it basically says, you do a case-insensitive query. So examples are really helpful to help generate cipher based on very typical queries. So we have our LLM, we have our examples, we then build our retriever. So our retriever has a connection to our database. It has an LLM. It's going to use that LLM to generate cipher, but also to generate responses to our questions. And we have a set of examples. And we build a GraphRAG pipeline, same as what we did with our vector plus cipher retriever. So we give it a retriever, we give it an LLM. We give it a query. So this is the thing I want to run. And we search for our query. And again, we're going to return the context. So the question I'm getting is, how many technologies are mentioned in the knowledge graph? This is a question that we should be able to answer from our knowledge graph using text decipher. So again, I'm going to run the process, and what it's going to do is it's going to go off and it's going to say, okay, well, turn that natural language question, how many technologies are mentioned, into a cipher statement. So it said, okay, well, match technologies and return a count of all of those technologies. The context that it got back was there's a technology count of 144, which it used to generate that response, which is correct. 144 technologies are mentioned in the knowledge graph. And using text decipher to answer very specific questions is something that, interestingly, vector search is very difficult to do. Because you can't search for how many technologies using a vector search. You have to return the whole knowledge graph, all of the information, in order to be able to do that. But by using text decipher, we can ask very specific questions. And there are, let's have a look at some further examples which are in the bottom of this lesson. How does Neo4j relate to other technologies? So let's just modify our query and we'll look at a couple of other examples. Let's just clear this. So same program, just a different query. How does Neo4j relate to other technologies? And again, it's going to go off, it's going to use our natural question, and it's going to generate bad cipher, I suspect, by the sounds of it. The above was following schema. So one of the things that we have to recognize about using, I'm trying to find the cipher statement that it created. It might not have output it. I hope it has. Yeah, so it's essentially generated in a badly formed cipher statement. One of the ways that we could fix that is that we could provide an example that allows the LLM to understand, okay, well, given the knowledge graph that I've got, how might I create a better formed cipher statement? I'm just going to try the other example. What entities exist? Okay, brilliant. Okay, right now. The knowledge graph currently contains records for the following entities types: benefits, challenge, chunks, concepts, documents, blah, 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 blah. Now, interestingly, we'll note that they are exactly the same node types that we defined when we created our knowledge graph. And we can see the cipher statement that it has created and the response that it returned that's allowed it to generate this response. Let's just try and find what resource URLs are referenced. So hopefully what it's going to do is it's going to look at that natural language question, generate a cipher statement, which it has. Let's come back with one. The context references in this resource URL, example.com. Fair enough. But we can see the cipher statement that it generated. Again, text decipher is an incredibly useful tool, particularly if you're looking to get information about what and if and how. Okay, so the final section in this workshop is all about agents. Now, what I'm going to do is I'm going to leave this for an activity for you to do, just while I have a quick look at questions and we'll close off. But what an agent is going to allow us to do is mix the different retrieval types that we have explored to generate context for our LLM to answer questions that it wants. And it's also going to allow us to dynamically call multiple tools or multiple retrievers in order to be able to answer one specific question. Okay. But yeah, activity for you to do yourself. So I am going to just have another moment to quick look at any questions if there are any. Joanna, I got 125. Yes, probably. Yeah, I mean, I can't remember what I got. Was it 122 or something like that? But again, it is again, given the non-deterministic approach of generative AI, your knowledge graph will look different to mine. Yeah, but yeah, I'm not surprised. But yeah, excellent. Okay. So yeah, thank you, Joanna. Okay, right. I'm going to find my slides again which is always difficult because I don't know where they've gone. And we'll just spend a couple of minutes bringing the session to an end and finishing on time. So, spent some time looking today at generative AI, looking at how Neo4j can support you in creating knowledge graphs that turn unstructured data into entities and relationships, and defining facts out of our unstructured data. Also looked at how we can add structured data to our knowledge graph to allow us to find additional and context that our LLM can use to provide a better response. Now, Graph Academy is full of courses that allow you to learn these concepts. What we have done today is an abridged version of about 3 or 4 different courses on Graph Academy. So it's been high in content, low in detail, intentionally, so that we get through and we can see how to implement these concepts in a short period of time. Graph Academy allows you to go much deeper into some of these subjects, look at how you can use your own data and use your own information to create a graph and to gain the benefits that we've looked at today. It is completely free. It is totally, there is a huge amount of hands-on work allowing you to learn about Neo4j, Cypher, generative AI, using our drivers in the language that you use, whether that's Python, .NET, JavaScript, TypeScript, insert name of language here that's useful to you. And you'll find lots of curated learning paths. You'll also find a free certification program so you can become Neo4j certified developer. So yeah, please spend time looking at Graph Academy. And then just to kind of note, I'll do a final kind of like if there are any questions before we finish, but our next session is going to be on Wednesday the 17th of June, and we're going to look at graph analytics and data science. So we're going to look at how we can use graph structures and graph data science algorithms to find insights within our data. So that will be our next session on the 17th of June in 2 weeks time. 2 weeks time. So I will just have a quick look, see if there are any questions. And then we'll draw things to a close. Iman, I'm misunderstanding regarding embedding technique. We use it for chunking the data and creating nodes. Could we use the prompts to understand the text and create nodes rather than just the embedding? So I'm not sure I understand your question. I misunderstand regarding embedding technique. We use it for chunking the data and creating nodes. Okay, so I think one thing to note is that we are throughout this process we have used 2 very different models. We have used a large language model. The large language model is the model that creates our responses and generates our text. We have used a second model, which is an embedding model. They are 2 different models. They are not to be confused with each other. So we used a large language model. That was the GPT-5 Nano, I think we used, and the embedding model, which was the text embedding model, small 3, I think we were using. Yeah, the embedding model's entire job is to turn text into vectors. It doesn't do any text generation. It just turns text into embeddings. So yeah, we use the LLM to generate our knowledge graph from our chunks of data, and we use the embedding model to turn the chunk text into vectors. So yeah, two different things. Could we use the prompts to create the text and create nodes rather than using embedding? So I think the question you're adding is, do we have to use the embedding model to query the graph? No, we don't. No, we do. We could, as we saw with text to cipher, create that embedding. We could create a query to query the graph directly. Just come back, understand the text and create nodes rather than using the embedding. Yeah, I think I understand what you're saying, which is you don't have to use the embedding model. I chose to because using vectors is a very powerful tool. Okay, So last but not least, we have lots and lots of events for you to join. You'll find everything on neo4j.com/events. You'll find live streams like these, you'll also find shorter sort of information sessions, as well as talking, conversational type live streams as well. You'll also find information about where Neo4j might be in terms of attending conferences, so where you can meet the Neo4j team and ask questions as well. Okay, last quick check. I think we're okay. Alex, is there anything that you wanted to say before we finished?
Thank you very much, Martin. No, I think you covered it all with these last couple of things. I added a survey, little slide out. If you have 2 minutes to spare, it would be nice if you could give us a little bit feedback of what you think of this workshop today. Any recommendations on future workshops, any topics you're interested in, any feedback in general, that would be always nice to hear. And yeah, like we said in the beginning and throughout, this was recorded. We will share links to the content, to the video, and to everything else with you within the next few days. So you can also repeat the session. And the course obviously is available on graphacademy.com. So you can always check out the other courses, but particularly this course, and if you want to do it in your own time. I saw a couple of people who said, well, they need to come back to here and follow it a little bit in their own speed, so that's totally possible. And yeah, I think with that, yeah, happy to see you on the 17th. I think that's the next workshop that's taking place around the topic. And yeah, if you have any questions, anything is unclear, the community is there for you. Check out Neo4j community space and reach out. And otherwise, see you around at a webinar, at a meetup, at a workshop, at a conference around you, and happy to talk to you and about graphs, obviously.
Thank you.
Thank you, Martin. Thank you, everybody, for watching and attending and for participating. And yeah, see you soon. Take care, everybody. Bye-bye.